In this video, we'll discuss various types of vulnerability assessment scanners. We'll discuss the common vulnerability scoring system and how scores are assigned to vulnerabilities. You will be able to describe the use of a Security Technical Implementation Guide, or a STIG, to enhance the overall security posture. And last, you'll be able to describe how to use the Center for Internet Security benchmark hardening / vulnerability checklists. Let's get started. According to the National Institute of Standards and Technology, vulnerability scanning identifies hosts and host attributes, like operating systems, applications, open ports, but it also attempts to identify vulnerabilities rather than relying on human interpretation of the scanning results. Vulnerability scanning can help identify outdated software versions, missing patches, and misconfigurations, and validate compliance or deviations from an organization's security policy. What is a vulnerability scanner? Vulnerability scanners are a software suite that have many capabilities whose main job is to assess a system for potential weaknesses that threats could expose. Capabilities of a vulnerability scanner include keeping an up-to-date database of all known vulnerabilities and exploits, detection of genuine vulnerabilities without excessive number of false positives. It has the ability to conduct multiple scans at the same time and perform trend analyses and create clear reports of the results. And they also provide recommendations for effective countermeasures to eliminate any discovered vulnerabilities. Vulnerability scanners are made up of four main components: engine scanners, databases, report modules, and the user interface. The engine scanner performs security checks according to its installed plugins, identifying system information and vulnerabilities. The built-in databases store all the vulnerability information, the scan results, and other data used by the scanner. The report module provides scan result reporting, such as technical reports for system administrators, summary reports for security managers, and high-level graph and trend reports for corporate executive leadership. And last, the user interface allows the administrator to operate the scanner. It may be either a graphical user interface, a GUI, or just a command line interface. Vulnerability scanners can exist either looking for internal threats or external threats. It's the difference of it scanning a host or the network. Internal threats, whether intentional or not, make up a large portion of attacks on a system. It could be through malware or a virus that is downloaded onto a network through internet or USB. It could be a disgruntled employee who has internal network access. It could be through the outside attacker who has gained access to the internal network. The internal scan is done by running the vulnerability scanner on the critical components of the network from a machine which is a part of the network. This important component may include a core router, switches, workstations, web server, databases, etc. On the other hand, the external scan is important as it is required to detect the vulnerabilities to those internet-facing assets through which an attacker can gain internal access. The external scan is done by running a vulnerability scanner on the host from the internet. It is always a good idea to eliminate the open issues or loopholes before it can be used and exploited by a malicious user or an attacker. One way to determine just how big of a threat something is to use the Common Vulnerability Scoring System. The Common Vulnerability Scoring System is a way of assigning severity rankings to computer system vulnerabilities, ranging from 0, least severe, to 10, most severe. The CVSS provides a standardized vulnerability score across the industry, helping critical information flow more evenly between sections within an organization and between organizations. The formula for determining the score is public and freely distributed, providing transparency. And it helps prioritize risk. The CVSS ranking provides both a general score and more specific metrics. The score itself is broken out into three main areas: a base score, a temporal score, an environmental score, which will provide the overall score of 0 through 10. The CVSS score has 3 values for ranking a vulnerability: a base score, which gives an idea of how easy it is to exploit the vulnerability and how much damage an exploit targeting that vulnerability could inflict; the temporal score, which ranks how aware people are of the vulnerability, what remedial steps are being taken, and whether threat actors are targeting it; and an environmental score, which provides a more customized metric specific to an organization or work environment. Let's break these down further. It should be noted that this will be a pretty high-level overview of the breakdown of the CVSS score. I highly recommend, after the video is over, to check out a CVSS score calculator where you can see all the different things that make up each subscore. With that being said, the base score is actually broken into 2 subscores: exploitability and impact. For the exploitability subscore, they take a look at the attack vector, the attack complexity, the privileges required, and what the user interaction was involved. The impact score has to do with the CIA triad. How does it impact the confidentiality, integrity, and availability of services? The temporal score takes a look at 3 things: the exploit code's maturity, the remediation level, and the report confidence. And last, the environmental score takes a look at the security requirements subscore, and then also takes into account an impact score of the CIA triad. Another assessment tool are the use of STIGs, Security Technical Implementation Guides. The Defense Information Systems Agency, or DISA, is the entity responsible for maintaining the security posture of the Department of Defense's IT infrastructure. Default configurations for many applications are inadequate in terms of security, and therefore DISA felt that developing a security standard for these applications would allow various DoD agencies to utilize the same standard, or STIG, across all application instances that exist. STIGs exist for a variety of software packages, including operating systems, database applications, open source software, network devices, wireless devices, virtual software, and the list continues to grow, now even including mobile operating systems. In order to view the most current STIGs, you can view the Department of Defense's public cyber exchange website. That's public.cyber.mil/STIGs. And here you can see the most current updates. You can download an application viewer. They have one for each operating system. So you can explore those databases and see what the most current security technical implementation guide is for any given application. The last vulnerability assessment tool we'll be discussing in this video is the Center for Internet Security's benchmark and controls. The CIS benchmark and controls are much like the STIGs in that they provide guidelines and recommendations for security settings and configurations for any given application or process. The difference is, instead of being from the DoD, it's from the security professionals and those in the industry. The CIS benchmarks are the only consensus-based best practice security configuration guides, both developed and accepted by government, businesses, industry, and academia. The initial benchmark development process defines the scope of the benchmark and begins the discussion creation and testing process of working drafts. Using the CIS Workbench community website, discussion threads are established to continue a dialogue until consensus has been reached on the proposed recommendations and the working drafts. Once consensus has been reached in the CIS benchmark community, the final benchmark is published and released online. The CIS controls are a prioritized set of actions that collectively form a defense in-depth set of best practices that mitigate the most common attacks against systems and networks. The CIS controls are developed by a community of IT experts who apply their first-hand experience in cyber as cyber defenders to create these globally accepted security-based practices. The 5 critical tenets of an effective cyber defense system, as reflected in the CIS controls, are: offense informs defense, prioritization, measurement and metrics, continuous diagnostics and mitigation, and automation. To be able to use the controls, you need to take a look at what implementation group your business or company falls under, and then compare that to the 20 different controls that the community has come up with. Let's take a look at those now. The implementation groups are defined by the company's security needs, 1 being the least amount or normal amount, and 3 being the maximum. So for the group 1, or the implementation group 1, the subcontrols for small, commercial, off-the-shelf, or home office software environments where sensitivity of the data is low and will typically fall here. Any implementation group 1 sub should also be followed by organizations in 2 and 3. And this will go for all of them, where 3 should be able to do 2 and 1, 2 should be able to do 2 and 1, 1 should be able to do just 1. For the second group, the subcontrols focused on helping security teams manage sensitive client or company information fall under here. And then for the largest security needs, they are the subcontrols that reduce the impact of zero-day attacks and targeted attacks from sophisticated adversaries. Typically, it's going to fall here. Now, these implementation groups will be applied to the 20 different control groups. So for each of these control groups, there will be a implementation group 1, 2, and 3 level response. So you can imagine there's a lot of different combinations. Let's go ahead and take a look at those now. Here are the 20 CIS controls. They're broken down into 3 categories: basic, foundational, and organizational. I'm not going to sit here and read you a list of 20. You can pause the video and read these, or you can go to the CIS's website and download in a PDF or Excel format to review these yourself. And that'll do it for this video on vulnerability assessment tools. Thanks for watching. We'll see you in the next video. In this video, we'll describe what port scanning is and what information we can gain from it. We'll also learn about the Nmap and Zenmap port scanning applications. Let's get started. According to the National Institute of Standards and Technology, network port and service identification involves using a port scanner to identify network ports and services operating on active hosts, such as FTP and HTTP, and the application that is running each identified service, such as the Microsoft Internet Information Server or Apache for the HTTP service. All basic scanners can identify active hosts and open ports, but some scanners are also able to provide additional information on the scanned hosts. Let's start with the basics. What is a port? Computer ports are the central docking point for the flow of information from a program or the internet to a device or another computer in the network, and vice versa. It's the parking spot for data to be exchanged through electronic, software, or programming related mechanisms. Ports 0 through 1023 are well-known port numbers that are designed for internet use. Although they can have specialized purposes as well, they're administered by the Internet Assigned Numbers Authority, or the IANA. These ports are held by top-tier companies like Apple, MSN, SQL Services, and other prominent organizations. You may recognize some of the more prominent ports and their assigned services, such as port 20, which is UDP, holds the file transfer protocol that we use for data transfer. Port 22 over TCP holds the SSH, Secure Shell Protocol, for secure logins, FTP, and port forwarding. Port 50 over UDP is the Domain Name System, DNS, which translates names to IP addresses. And port 80 over TCP, which is the worldwide HTTP. Now, numbers 1024 through 49,151 are considered registered ports, meaning they are registered by software corporations. And then 49,151 through 65,536 are dynamic and private ports and can be used by nearly everyone. Now, these ports, when engaged, all solicit a response. So a port scanner is a simple computer program that checks all of those open ports in response with one of three possible responses: open, closed, or filtered, dropped, blocked, etc. If the port is open or it accepts the ping, the computer responds and asks if there's anything it can do for you. If it's closed or just not listening, the computer responds acknowledging that it's there, but that the port is currently in use and unavailable at this time. Now, if it's filtered or blocked, the computer doesn't even bother to respond, and you get zero input from it. Port scanning is a method of determining which ports on a network are open and could be receiving or sending data. It is also a process for sending packets to specific ports on a host and analyzing that response to be able to identify any vulnerabilities. There are 5 common types of scans that we're going to cover here. The first type of scan is just the ping. It's the simplest port scan, sending an ICMP echo request to see who's responding. The next one is arguably the most popular. It's the TCP half-open scan. It's popular because it's very deceptive and it's very sneaky. It's also known as an SYN scan or sync scan. It notes the connection from the ping, but it leaves the target hanging. So you get information from the ping, but the host does not get that information. Now, its counterpart, the TCP connect, takes that a step further by completing the TCP connection. This makes it slower and noisier, meaning it's easier to detect. The next type of scan is a UDP scan. Now, when you run a UDP port scan, you send either an empty packet or a packet that has a different payload per port, and you will only get a response if the port is closed. It's faster than TCP, but doesn't contain as much data. And last is a stealth scan. Now, these TCP scans are quieter than all the other options and can get past firewalls, but are still going to get picked up by the most current intrusion detection systems. This leads us to one of the most popular port scanning applications, Nmap. Now, Nmap stands for Network Mapper and is an open source tool for network exploration and security auditing. It was designed to rapidly scan large networks, although it works fine against a single host. Nmap uses raw IP packets in novel ways to determine what hosts are available on the network, what services, application name and version, those hosts are offering, and what operating system and version of they are running, and what type of packet filters or firewalls are in use, and dozens of other characteristics. While Nmap is commonly used for security audits, many systems and network administrators find it useful for routine tasks, such as network inventory, managing service upgrade schedules, and monitoring hosts or service uptime. And last is Zenmap, which is still made by Nmap, but provides a graphical user interface. This makes the representation of data a lot more useful and the overall application much easier to use. In this video, we'll learn what network protocol analyzers are, and we'll learn about Wireshark as the predominant protocol analyzer. And then we'll seek to understand the packet capture file format. Let's get started. A protocol analyzer, also known as a sniffer, packet analyzer, network analyzer, or traffic analyzer, can capture data in transit for the purpose of analysis and review. Sniffers allow an attacker to inject themselves in a conversation between a digital source and destination in hopes of capturing useful data. These network sniffers operate at the data link layer of the OSI model, which means they do not have to play by the same rules as the application and services that reside further up the stack. Sniffers can capture everything on the wire and record it for later review. They allow users to see all the data contained in that packet. The leading sniffer out there? Wireshark. Wireshark intercepts traffic and converts that binary traffic into human-readable format. This makes it easy to identify what traffic is crossing your network, how much of it, how frequently, and how much latency there is between certain hops, and so forth. Wireshark is used by network administrators to troubleshoot network problems, by security engineers. They use it to examine security problems. QA engineers use it to verify network problems. Developers use it to debug protocol implementations. And people in general can use it to learn about network protocol internals. For being freeware, Wireshark hosts an impressive amount of features. It has deep inspection of hundreds of protocols, with more being added all the time. It offers live capture and offline analysis. It comes standard with a 3-pane packet browser. It runs across multiple platforms: Windows, Linux, Mac OS, FreeBSD, BSD, etc. The captured data can be browsed via a graphical user interface or via the TTY mode, T-Shark utility. It has the most powerful display filters in the industry, as well as a rich voice over IP analysis. It reads and writes many different capture file formats. The capture files are compressed with gzip and can be decompressed on the fly. Live data can be read from many different media sources. Decryption support for many protocols, including IPsec, ISAKMP, Kerberos, SMP v3, SSL TLS, WEP, and WPA, WPA2. The coloring rules can be applied to the packet list for quick, intuitive analysis. Output can be exported to XML, PostScript, CSV, plaintext, and many more. What makes Wireshark so impactful is the data that it captures. Now, packet capture or PCAP, is a valuable resource for file analysis in monitoring your network traffic. Packet collection tools like Wireshark allow you to collect network traffic and translate it into a format that's human readable. There are many reasons why PCAP is used to monitor networks. Some of the most common include monitoring bandwidth usage, identifying rogue DHCP servers, detecting malware, DNS resolution, and incident response. And Wireshark is the most popular traffic analyzer in the world. Wireshark uses the PCAP files to record packet data that has been pulled from a network scan. The packet data is recorded in files that are in the .pcap file extension and can be used to find performance problems and cyber attacks on networks. Now, the packet capture, or the PCAPs, come in 4 different file format variants. The first of which is going to be the libpcap, LIB standing for library PCAP. This is going to be used in Unix-based systems such as Linux and Mac OS. WinPCAP is the variant for the Windows operating system, and while it can be read by Wireshark, is kind of an old format that is not used by default anymore. Now, PCAP NG is next generation. This is the default format that Wireshark will capture packets in, and is considered next generation because it both captures and stores data. And the last is NPCAP, which is only used by Nmap, a port scanning application that has the ability to capture packets as well.
This is a series of 4 short videos that will be used to describe security architecture concepts. The first video will explain the characteristics of a security architecture, including why architectural thinking is important. The next video will go on to discuss different types of high-level security architecture representations that can be used and when to use them in practice. The third video will go on to look at how to describe security solutions as they are decomposed to identify threats and specify the required security controls. In the final video, I will discuss how security patterns can be used to accelerate the development of security for infrastructure and applications. So let's start this video by explaining the characteristics of security architecture. I believe architecture forms the foundation of good security. How you put the security together is just as important as what security controls are used and how they're managed. This house you see is the Winchester Mystery House and is a good example of how not to construct a house. Sarah Winchester inherited $20 million on the death of her husband. She recruited a dedicated crew of carpenters to build 160 rooms so quickly that nobody bothered to draw up blueprints. And she didn't hesitate to make unorthodox building decisions. A stairway ascending to a wall, a closet about an inch deep, and a door to nowhere that opens to empty space. This is a good example of how not to build a complex system without an architect to define how the components of the house are to be put together, and a project manager to ensure it is built to specification. This is also true of security architecture. It is needed to provide assurance that the solution has been designed and constructed effectively, integrating each of the components into a system. So build with a clearly communicated structure. The second lesson is about a Raspberry Pi. The Jet Propulsion Labs in the US perform sensitive research but also needs to be connected to the internet. In 2018, an employee brought in their own Raspberry Pi and bridged the internal network with the internet, allowing hackers to extract around 500 megabytes of data. It was found there were many shortcomings with the JPL security, including a lack of a mechanism to detect unauthorized devices on the network and insufficient networking segmentation. They could have done a better job of systematically assessing the potential threats and designing the controls to meet those threats. So systematically analyzing threats and controls would have helped. Finally, don't build security like this security gate. Let's talk about the complexity and where security architecture is most effective. When a shed is constructed, it can be completed with one person and planned with a list of components on a scrap of paper. With a house, there will be a team of skilled professionals, including an electrician, plumber, carpenter, etc. They will work to a solution provided by an architect and managed by a project manager. As the complexity increases, as with these high-rise buildings in Hong Kong, there will be many teams of people involved in the construction. Different techniques and tools will be used. Plans will be at differing levels of abstraction, with high-level architecture showing the overall solution without any specific details. This high-level architecture will be decomposed into a design for each building, a design for each floor, and then a design for each flat or apartment. Rather than creating a separate design for each floor and flat, a series of patterns will be defined that can be reused. Patterns provide a rapid way of developing similar systems or components. Special solutions will be developed for the different professions. There may be a solution for electricity, a solution for plumbing. There are different viewpoints of the same overall solution, with more detail for a specific profession. The same approach is used with IT architecture, with differing levels of abstraction targeted at different members of the team designing, delivering and operating the system. There might be an architecture diagram for the overall system, with decomposition to more and more detail until there are documents describing how to install hardware in a rack. There will be different viewpoints. One of those viewpoints will be security, to identify the security capabilities within a system. Each document describing the solution will need to be integrated with other viewpoints across the team, whether it's storage, platform, or availability. All of this should use a systematic approach to communicate an architecture that is created using a standard set of tools and techniques. Using a standard way of communicating will enable team members to ensure a robust system is constructed. Let's look at architectural thinking. Architectural thinking is about creating and communicating good structure and behavior, with the intent of avoiding chaos. In IT systems, we talk about the architecture being described using different levels of abstraction, covering both the implementation and the operations. This needs a careful balance, as a solution needs to be affordable and yet secure. There are many ways to describe an architecture, but essentially the architecture will be made up of a static structure and a dynamic behavior. What does that mean? The static structure describes how the components will be connected together. If I connect two components together using a wire, it doesn't mean it will perform a useful function. The dynamic behavior describes how the components will interact over time, including how the communication is secured. As a system is put together, There is a series of design decisions that shape the system, balancing security, usability, resilience, and cost. As a security architect, you need to consider security does not override the other characteristics needed in a system. That's it for now. In the next video, you will get to understand the different types of architectural models and when to use them. Welcome back to the unit on security architecture concepts. In the last video, we discussed how architecture is important to the construction of robust security. In this video, we will continue our conversation on concepts that will help you describe your high-level security architecture. I will explain the characteristics of a high-level security architectural models, discuss the different representations at different levels of abstraction, and when to use the model in practice. Architecture is defined as the art of building. When buildings are being constructed, they often start with an overall picture that gives the visual idea of what the building will look like. It does not define how the building will be constructed and tells us little about the context. In this example, for a building, it does give us a little bit of context in terms of contour lines and a lake, but it does not tell us the details that would allow us to construct the building. In IT architecture, this is what could be considered as an enterprise level architecture. There will be further drawings that will give detail on the context and the implementation of the system. Let's start with different types of high level architecture. We can break the problem down into further levels of abstraction: enterprise architecture and solution architecture. First, the enterprise architecture considers a wide scope for the whole enterprise. It shows the main components of the problem space at a very high level with a small number of components. It might show some interrelationships and context, but a very high level. It could show processes, high-level business services, or different domains. The representation is very loose. As we decompose the problem, we need to go and add context and technology components. We start to move into solution architecture. Now we start to add the context about the environment and the technology perspectives. The architecture diagrams become more complex. Let's look at how we represent these architectures. We use what is called building blocks. These will be used to represent a business need. It could be a capability, domain, act, or a business service. These building blocks are there to represent a grouping that is loosely coupled. At an enterprise level, architectural building blocks, or ABBs, are high-level guiding components guiding the development of the solution architecture. The ABBs are product and vendor neutral. At the solution architecture level, solution building blocks, or SBBs, specify technical components or particular products to implement a function. Context is added in terms of the platforms and the environments. They may be product or vendor aware. Let's look at some example building blocks. In this example, we have 5 high-level architecture building blocks. They are general security domains like data and application security. They are not specific security functions. And the solution building blocks show security functions such as certificate authority or application firewall, but are not specific to any vendor or product in this example. Let's look at an example enterprise architecture. This is a high-level example of an enterprise security architecture for hybrid multi-cloud, with architectural building blocks showing there are 5 domains for logical security that are supported by physical security. As this is about security for multiple clouds, it shows integration takes place with multi-cloud security management with oversight through governance, risk, and compliance. This is good as a high-level set of domains to help organize projects or decompose problems, but it tells us nothing about the context of technology, capabilities, or environments. So let's look at another example. In this example of an enterprise architecture, we start to add groupings of security capabilities to provide more detail on the composition of each domain, but it still doesn't have any context. This can be useful as a heat map to describe the maturity of capabilities being delivered. I've seen organizations use this sort of diagram to assess maturity and then color the capabilities red, amber, or green to enable a focus on remediation of security controls. Let's go on to look at the next level of detail. In this enterprise security architecture, we've taken the security domains and split them into security controls built into the cloud infrastructure and security added on top of the cloud infrastructure. With the built-in security domains, the controls can be deployed onto network, compute, and storage platforms that are then decomposed further. For networking, the controls can be in the physical underlay network, software-defined overlay network, and the container communication using a service mesh. Then each of these platforms can be deployed into different environments: on-premise in a corporate data center, a private cloud, a public cloud, and on-edge computing servers. The same security domains are used for the built-in security and the add-on security, as every cloud is different in what is included, and often security will be needed as an add-on. Across the top, the picture shows multi-cloud security management again, to integrate each of the environments. Overall, governance, risk and compliance is needed to ensure security is working effectively. This sort of architecture diagram is used to describe the dimensions of the different perspectives of security controls that need to be considered in the context of that IT environment. In this case, it helps a security architect describe the complexity of the security controls in a hybrid multi-cloud environment. It can be used to discuss the need for a common IT and security platform across the different environments. Otherwise, this gives rise to complexity, resulting in increased cost and reduced effectiveness of security. All of these architecture diagrams you'll see in a very high level. They don't describe the physical implementation. In the next video, you'll get to understand further representations of a solution architecture, as the solution is decomposed into specific implementations of a solution. That's it for now. I'll speak to you in the next video about decomposing the solution architecture. Welcome back to the unit on security architecture concepts. In the last video, we discussed concepts that will help you describe your enterprise security architecture. In this video, we'll continue our conversation on concepts that will help you describe your security solution architecture. I will explain the solution architecture models, discuss the different representations at different levels of abstraction, and when to use the representation in practice. During the development of the solution architecture for security, the threats will be identified and the specific controls specified. Architecture develops through a series of steps decomposing from an overall enterprise architecture to specific solutions. This slide shows the differing levels of representation from the overall enterprise architecture to the detailed operational model, specifying the different hardware components. There is an overlap between the different architectures, so don't expect a clean boundary, as sometimes hybrid versions of diagrams are used. These diagrams will be used from two perspectives: as a security architect supporting a solution being developed by a wider team, or as a security architect designing a security service where all the aspects of IT architecture need to be considered. This video is going to focus on specifying security for a solution, with an architecture overview, system context, functional model, and operational model. Before doing that, you might like to pause the video just to consider the different layers that are part of this architecture. Once you have an idea of the solution required to be designed and delivered, document an architecture overview as a high-level conceptual diagram. The diagram has no specific format and needs to be sufficient to communicate the concepts of what you're trying to develop. It enables a project to be initiated with an initial view of the system, but the diagram doesn't consider security yet. Security can be considered by first identifying the boundary of the system, with actors external to the system. These actors can either be human or system actors. The actors each perform activities that are described for use cases. These use cases process data that will flow to and from the system. It is this data and the availability to perform these use cases that the security controls are protecting. Therefore, creating a system context will document the external data flows needed for protection and think about the actors and the use cases. We can then classify the sort of data being processed, and based on policy, this will guide the security controls needed with the environments that may be used. This is useful, and once we know this, we can think about the security inside the system. The actors and data flows external to the system initiate data flows inside the system. Therefore, the next step is to document the functional components of a system and the interactions between those components. Each of those interactions will include a data flow. At this level, we can also look at the threat actors within the system and start to identify the controls needed to protect the data in transit and at rest. At this level, we're documenting the application functionality, but not how the system will be implemented and operated. We need another diagram for that. The capabilities needed to implement the application functionality needs to be identified. Based on the classification of the data and the specific implementation, components are placed into zones with different data classifications. Based on the organizational policies and standards, the security controls will start to be identified to a particular technology or product at this level. Is the requirement for Flash or Windows 2003 acceptable in your organization? It's these sorts of decisions that will need to be discussed. To support the environment, new actors may start to be identified, such as security operations. Is this capability outsourced or operated in-house? If operated outsourced, then the security context will need to be updated to include a new actor. The actor will have new use cases and data that will need to be protected in transit and at rest. There's lots more that needs to be considered, but I hope this gives you an insight into the systematic way of thinking about security using architecture thinking. As the architecture is elaborated, some questions to ask perhaps are: who are the stakeholders or actors to enforce the security? Where are the locations for each of the systems, components and actors? When are the security controls required, ideally with some sort of priorities for implementation? Why is the system needed? This can help prioritize controls and their implementation. What is it that needs to be protected? How will the data need to be protected? Thinking about all these sorts of questions will be an iterative process, with earlier diagrams updated and then later diagrams then updated to reflect those requirements and those new improvements. That's it for now. I'll speak to you in the next video about accelerating the solution through the use of different security patterns. For this unit, we'll continue our conversation by discussing how patterns can be used to accelerate the design of systems. I've described different practices, but many people have been through this thinking in the past. They've applied best practices to create patterns that will accelerate development. An architecture pattern is a reusable solution to a commonly occurring problem. It provides a template based on best practice to solve part of the problem for you. A pattern is not a complete solution because it doesn't take into account the context of the specific solution. Patterns come in many different formats. At a high level, this example from the IBM Cloud architecture can provide a starting point. Sometimes patterns are supplied by software vendors on how to use their software, and in other cases the pattern is agnostic. The patterns demonstrate the way the software is supposed to be used, and it provides a shortcut. There are many more generic patterns available that will help providing different levels of detail. Some may go as far as the IBM Red Books to document complete tested solutions that describe how to put them together. Always look for common patterns before starting your design to help identify best practices and shorten your development lifecycle. Finally, let's reflect on what has been taught in this unit. I discussed the characteristics of a security architecture. As IT systems increase in complexity, we need a standard set of tools and techniques that will enable us to communicate good structure and behavior with the intent of avoiding chaos. We saw chaos in the Winchester Mystery House and don't want a repeat of this with systems that we build. I discussed the different high-level architecture models. An enterprise architecture can be used to communicate at an organization level an overview of the system components without getting into the implementation detail. I demonstrated 3 different perspectives and talked about how they can be used. I discussed the solution architecture, helping us to identify the threats and the controls needed to protect data in transit and at rest. There are diagrams at different levels of abstraction that will help us in this architectural thinking process. And I discussed how to accelerate the design of solutions by making use of proven architecture patterns. So that's the end of the final video and the unit. Thanks for listening and good luck with architecting security into your solutions.
In this video, you will learn to summarize key terms important to application security, describe the pros and cons of various software development life cycles, explore application security risks, and discuss application security techniques, dynamic analysis, static source code analysis, and industry tools. Let's take a look at the definition of application security. Application security encompasses measures taken to improve the security of an application, often by finding, fixing, and preventing security vulnerabilities. Different techniques are used to surface such security vulnerabilities at different stages of an application's lifecycle, such as design, development, deployment, upgrade, and maintenance. Before we review the application's lifecycle, let's make sure we understand some key terminology and how application security fits with overall information security that we have covered in other courses and modules. So what is the difference? Network security is a protection of systems and information assets at the network level, typically involving areas such as routers and switches, servers, workstations, and wireless networks. Technologies such as firewalls, intrusion prevention systems, and data loss prevention are put in place to keep these systems protected. Additionally, patch management tools and vulnerability scanners to discover and prevent security weaknesses at the network level, all topics we have discussed previously in this course. Application security, however, is the protection of application front ends, source code and information assets at the software level, involving systems such as websites, databases, mobile apps, and client and server applications. Technologies such as web application firewalls and source code analyzers are used to secure applications. Operating systems such as Windows, Mac OS, and Linux technically fall into both categories, but would typically be considered a part of network security. Both network security and application security are components of an overall information security program that includes policy, procedures, incident response, and disaster recovery. Regardless of the specific threats and vulnerabilities associated with network systems and application environments, both network and application security work together to support the greater good of the business and overall IT risk mitigation. A couple of other terms we should review in regards to application security. Threat is the potential for a security violation and the harm it will cause. If you have a data center in California, earthquakes are a threat. In application security, the biggest threats are malware and hackers. Risk is the likelihood of an attack. Compare the risk of an earthquake hitting a data center in San Francisco with a data center in Chicago. In application, risk is the likelihood a malware or hacker attack the confidentiality, integrity, or availability, the CIA triad, of an application. Vulnerability is a security flaw in code. Known software vulnerabilities can be patched to reduce the risk of an attack. Unknown software vulnerabilities or zero-day vulnerabilities are harder to defend against. Different techniques will find different subsets of the security vulnerabilities lurking in an application and are most effective at different times in the software lifecycle. They each represent different trade-offs of time, effort, cost, and vulnerabilities found. We will explore some of these techniques later in this lesson. Utilizing these techniques appropriately throughout the software development lifecycle will maximize security in the role of an application security team. You will see variations of the software development lifecycle of plan, develop, test, deploy, and maintain, depending on your organization's specific guidelines. Each may refer to the different phases uniquely, and each organization will determine its software development methodology that works best for its software or is recommended within its industry. Here are the most common software development methodologies. Waterfall is a top-down development approach which was most common in the past. It is simple and easy to follow, but not very flexible, and design flaws can be costly if discovered after the application is deployed. Agile, unlike the top-down approach of Waterfall, consists of short bursts of analysis, design, coding, and testing. This methodology is responsive and motivates the team to be productive. However, driven by the pressure to meet the cycle deadlines, it is easier to forget application security testing. Scrum is agile development, focusing on a sprint of 1 to 4 weeks typically. Like Agile and Scrum, the spiral software development methodology was invented with response to the perceived limitations of the top-down waterfall methodology. It focuses on minimizing risk, which makes it possible to evaluate security at the end of each cycle. However, it is not as quick as Agile, which may increase the cost of the software development. The iterative form of software development breaks up development into smaller prototypes through repeated cycles, which allows lessons to be learned from earlier iterations. However, if the planning cycles are too short, certain security needs may be missed. During application testing, penetration testing should take place to test the software for vulnerabilities. Pen testing falls into 3 categories. White box testing. White box testing provides the attackers with detailed information about the systems they target. This bypasses many of the reconnaissance steps that normally precede attacks, shortening the time of the attack and increasing the likelihood that it will find security flaws. Black box testing. Black box testing, which does not provide attackers with any information prior to the attack. This simulates an external attacker trying to gain access to information about the business and technical environment before engaging in an attack. Gray box testing, known as partial knowledge tests, are sometimes chosen to balance the advantages and disadvantages of white and black box penetration tests. Most common when black box results are desired, but cost or time constraints mean that some knowledge is needed to complete this testing. Common technologies used for identifying application vulnerabilities include static application security testing, which is a technology that is frequently used as a source code analysis tool. The method analyzes source code for security vulnerabilities prior to the launch of an application and is used to strengthen code. This method produces fewer false positives, but for more implementations requires access to the application's source code and requires expert configuration and lots of processing power. Dynamic application security testing is a technology which is available to find visible vulnerabilities by feeding a URL into an automated scanner. This method is highly scalable, easily integrated, and quick. DAS drawbacks lie in the need for expert configuration and the high possibility of false positives and negatives. Interactive application security testing is a solution that assesses applications from within using software instrumentation. This technique allows IS to combine the strengths of both SAS and DAS methods, as well as providing access to code, HTTP traffic, library information, back-end connections, and configuration information. Some IS products require the applications to be attacked, while others can be used during normal quality assurance testing. In this video, you will learn to explore application threats and attacks, and summarize the OWASP Top 10 Application Security Risks. In our discussion so far, we have been discussing applications developed in-house, but what about third-party applications? Before an organization selects any third-party software, especially mission-critical software, an application security professional should assess the risk and ask questions about the security standards used to develop the software. It is also important to know about security patching and any testing standards used by the third party. The formal process of analyzing the risk to an organization's business of acquiring a third-party software is called a supplier risk assessment or vendor risk assessment. The first step is to identify how any risk would impact your organization's business. It could be a financial, operational, or strategic risk. Next step would be to determine the likelihood the risk would interrupt the business, and finally there is a need to identify how the risk would impact the business. Some risks may be too high that either a business process might change or another software may need to be evaluated. Another important element of application security is installing a Web Application Firewall, or WAF. A Web Application Firewall filters, monitors, and blocks HTTP traffic to and from a web application. A WAF is differentiated from a regular firewall in that a WAF is able to filter the content of specific web applications, while regular firewalls serve as a safety gate between servers. By inspecting HTTP traffic, it can prevent attacks stemming from web application security flaws such as SQL injection, cross-site scripting, file inclusion, and security misconfigurations. What are some of the most common threats and the associated attacks for applications? Input validation. Attacker modifies an existing application's runtime behavior to perform unauthorized actions, exploited via binary patching, code substitution, or code extension. Some common attacks are cross-site scripting, which we will explore deeper in a later lesson, SQL injection, which we have explored in an earlier course, and buffer overflow. Authentication is the process that verifies the identity of the individual. Some common attacks are brute force attack, credential theft, and network eavesdropping. Authorization is a function of specifying access rights and privileges to resources. A very common authorization attack is elevation of privilege. We will see several examples of this in the next course around breaches. Configuration management. Typical configuration management attacks include unauthorized access to administration interfaces, unauthorized access to configuration stores, retrieval of clear text configuration data, lack of individual accountability, and overprivileged process and service accounts. Exception management threat, like a denial of service attack, is a cyber attack in which the perpetrator seeks to make a machine or network resource unavailable to its intended users by temporarily or indefinitely disrupting services of a host connected to the Internet. Finally, auditing and logging is another common threat for applications. Some attacks include user denies performing an operation, attacker exploits an application without trace, or an attacker covers his or her tracks. There are many industry resources that should be consulted when working in an application security role. Let's look briefly at the OWASP Top 10 Web Application Security Risks. Injection. Injection flaws occur when untrusted data is sent to an interpreter as part of a command or query. The attacker's hostile data can trick the interpreter into executing unintended commands or accessing data without proper authorization. Broken authentication. Application functions related to authentication and session management are often implemented incorrectly, allowing attackers to compromise passwords, keys, or session tokens, or to exploit other implementation flaws to assume other users' identities temporarily or permanently. Sensitive data exposure. Many web applications and APIs do not properly protect sensitive data such as financial, healthcare, and PII. Attackers may steal or modify such weakly protected data to conduct credit card fraud, identity theft, or other crimes. Sensitive data may be compromised without extra protection, such as encryption at rest or in transit, and requires special precautions when exchanged with the browser. XML external entities. Many older or poorly configured XML processors evaluate external entity references within XML documents. External entities can be used to disclose internal files using the file URI handler, internal file shares, internal port scanning, remote code execution, and denial of service attacks. Broken access control. Restrictions on what authenticated users are allowed to do are often not properly enforced. Attackers can exploit these flaws to access unauthorized functionality and/or data such as access other users' accounts, view sensitive files, modify other users' data, or change access rights. Security misconfiguration. Security misconfiguration is the most commonly seen issue. This is commonly a result of insecure default configurations, incomplete or ad hoc configurations, open cloud storage, misconfigured HTTP headers, and verbose error messages containing sensitive information. Not only must all operating system frameworks, libraries, and applications be securely configured, but they must be patched, upgraded, and upgraded in a timely fashion. Cross-site scripting. Cross-site scripting flaws occur whenever an application includes untrusted data in a new web page without proper validation or escaping, or updates an existing web page with user-supplied data using a browser API that can create HTML or JavaScript. Cross-site scripting allows attackers to execute scripts in the victim's browser, which can hijack user sessions, deface websites, or redirect the user to malicious sites. Insecure deserialization. Insecure deserialization often leads to remote code execution. Even if deserialization flaws do not result in remote code execution, they can be used to perform attacks, including replay attacks, injection attacks, and privilege escalation attacks. Using components with known vulnerabilities. Components such as libraries, frameworks, and other software modules run with the same privileges as the application. If a vulnerable component is exploited, such as an attack, can facilitate serious data loss or server takeover. Applications and APIs using components with known vulnerabilities may undermine application defenses and enable various attacks and impacts. And finally, insufficient logging and monitoring. Insufficient logging and monitoring, coupled with missing or ineffective integration with incident response, allows attackers to further attack systems, maintain persistence, pivot to more systems, and tamper, extract, or destroy data. Most breach studies show time to detect a breach is over 200 days, typically detected by external parties rather than internal processes or monitoring. In this video, you will learn to explore standards and regulations for application security. I want to spend a couple of minutes on threat modeling before we have a standards and compliance review. Threat modeling is a process by which potential threats, such as structural vulnerabilities or the absence of appropriate safeguards, can be identified, enumerated, and mitigations can be prioritized. The purpose of threat modeling is to provide defenders with a systematic analysis of what controls or defenses need to be included, given the nature of the system, the probable attacker's profile, the most likely attack vectors, and the assets most desired by an attacker. Numerous threat modeling methodologies are available for implementation. Typically, threat modeling has been implemented using one of four approaches: independently, asset-centric, attacker-centric, and software-centric. Let's discuss a few of the most well-known methodologies. The STRIDE approach to threat modeling was introduced in 1999 at Microsoft, providing a mnemonic for developers to find threats to our products. STRIDE patterns and practices and Asset Entry Point were amongst the threat modeling approaches developed and published by Microsoft. PASTA stands for the Process for Attack Simulation and Threat Analysis. which is a 7-step risk-centric methodology. It provides a 7-step process for aligning business objectives and technical requirements, taking into account compliance issues and business analysis. The intent of the method is to provide a dynamic threat identification, enumeration, and scoring process. Once the threat model is completed, security subject matter experts develop a detailed analysis of the identified threats. Finally, appropriate security controls can be enumerated. This methodology intended to provide an attacker-centric view of the application and infrastructure from which defenders can develop an asset-centric mitigation strategy. Trike. Next, the focus of the Trike methodology is using threat models as a risk management tool. Within this framework, threat models are used to satisfy the security auditing process. Threat models are based on requirements model. The requirements model establishes the stakeholder-defined acceptable level of risk assigned to each asset class. Analysis of the requirements model yields a threat model from which threats are enumerated and assigned risk values. The completed threat model is used to construct a risk model based on asset, roles, actions, and calculated risk exposure. Finally, VAST is an acronym for Visual, Agile, and Simple Threat Modeling. The underlying principle of this methodology is the necessity of scaling the threat modeling process across the infrastructure and entire SDLC and integrating it seamlessly into an agile software development methodology. The methodology seeks to provide actionable outputs for the unique needs of various stakeholders, application architects and developers, cybersecurity personnel, and senior executives. The methodology provides a unique application and infrastructure visualization scheme such that the creation and use of threat models do not require specific security subject matter expertise. Security standards and regulations are important in all security domains, but may be the most important in stopping attacks within your organization. Here are a few of the additional standards you should become familiar with as an analyst or any cybersecurity profession. The CERT C coding standard is the software coding standard for the C programming language, developed by the CERT Coordination Center, and should be used to improve the safety, reliability, and security of software systems. The Computer Emergency Response Team, or CERT, for the Software Engineering Institute is a nonprofit United States federally funded research and development center. The Common Weakness Enumeration, or better known as the CWE, is a category system for software weaknesses and vulnerabilities. It is sustained by a community project with the goals of understanding flaws in software and creating automated tools that can be used to identify, fix, and prevent these flaws. The project is sponsored by the National Cybersecurity, FFRDC, which stands for Federally Funded Research and Development Center, and is operated by the MITRE Corporation with support from U.S. CERT and the National Cybersecurity Division of the U.S. Department of Homeland Security. The Defense Information Systems Agency has put together a security technical implementation guide as a cybersecurity methodology for standardizing security protocols within networks, servers, computers, and local designs to enhance overall security. These guides, when implemented, enhance security for software, hardware, physical, and logical architectures to further reduce vulnerabilities. Another set of standards for application security are from the International Organization for Standardization, ISO, and are part of the overall information security management set of standards, specifically ISO 27034, which describes the minimum requirements when the required activities specified by an application security control, or ASC, are replaced with a prediction application security rationale, or PASR. The ASC mapped to a PSR define the expected level of trust for a subsequent application. And ISO 24772, which is a standard around information technology, programming languages, which provides guidance to avoiding vulnerabilities in programming languages through language selection and use. Another financial institute standard, PCI Data Security Standard, or PCI DSS, is mandated by the card brands but administered by the Payment Card Industry Security Standards Council. The standard was created to increase controls around cardholder data to reduce credit card fraud. And finally, NIST Special Publication 800-53 provides a catalog of security and privacy controls for all U.S. federal information systems, except those related to national security. It is published by the National Institute of Standards and Technology, which is a non-regulatory agency of the United States Department of Commerce. Compliance controls and testing also play an important part in application security. I will review a few of the governing regulations you should be aware of as a cybersecurity professional. Most may be a review, but are worth mentioning. The Gramm-Leach-Bliley, or GLBA, is also known as the Financial Services Modernization Act of 1999. Until the GLBA became law in 1999, there were strict governmental boundaries between financial institutions. Banks, insurance companies, and credit card providers were severely limited in the services they could provide and the information they could share with each other. GLBA somewhat relaxed the regulations, which caused concern with this increased latitude, which could have far-reaching privacy implications. Because of this concern, it included a number of limitations on the types of information that could be exchanged even among subsidiaries of the same corporation. The Health Insurance Portability and Accountability Act of 1996 was created primarily to modernize the flow of healthcare information, stipulate how personally identifiable information maintained by the healthcare and healthcare insurance industries could be protected from fraud and theft, and address limitations on healthcare insurance cover. The Sarbanes-Oxley Act of 2002, or SOX, is a United States federal law that set new or expanded requirements for all U.S. public company boards, management, and public accounting firms. A number of provisions of the Act also apply to privately held companies, such as the willful destruction of evidence to impede a federal investigation. All of these regulations are in addition to regulations that we've already covered in the compliance section of an earlier course. As you can see, developing based upon security guidance and compliance are both an important part of application security. In this video, you will learn to understand the concept of DevOps and automation and its effect on application security. With the use of cloud comes the expectation that innovation and provisioning is sped up. Traditionally, security checks and testing has been seen to decrease this velocity. So organizations must now look at how they can ensure their deployments are secure, but that rapid innovation is not inhibited. In order to facilitate rapid development, innovation, and provisioning, security practices must keep up with the agile-paced cloud of the cloud era. Planning cycles are shorter with more frequent deployments and more iterations as required. Deployments are becoming smaller in nature and following a more standardized approach through consistent pipelines. Reduction in time from build to deployment is being enabled by automation and self-service. A level of autonomy is being afforded to teams. DevOps came about because development teams primarily focused on producing new systems, applications, and functionality, and making them available to consumers as quickly as possible. Operations, on the other hand, look from a different aspect altogether. Their primary focus is on ensuring a responsive and stable system. The DevOps philosophy bridges this gap and fosters integration, collaboration, and communication to ensure a balance between development and quality. The development engineers are developing rapidly and autonomously. They are working alongside the operations engineers to ensure quality deployments that are bug-free. But what about secure and vulnerability-free apps? What about ensuring compliance with regulations that potentially keep changing? What about ensuring there is protection against and accountability of all development to protect data and intellectual property? Both DevOps and security engineers want easily deployable, vulnerability-free releases. They also want automation and integration to achieve this with minimum requirement to reskill and minimum overhead. This is why DevOps needs to morph into DevSecOps, where security, integration, and automation are key. DevSecOps is the integrated, automated, continuous security, always. Integrating security with DevOps is DevSecOps. Here is one approach. The IBM DevSecOps reference architecture isn't just a technical framework encompassing people's mindset and culture, and alignment with strategy, governance, risk, and compliance. The framework guides how to develop securely and run secure operations, embedding security and continuous learning to transform DevOps into DevSecOps. We shall consider each of the framework elements in more depth over the coming slides. Alignment with strategy and governance plays a central role in the design of systems and their components. Checks can be put in place to continually assure requirements are being adhered to. Risk is a continual factor in any IT systems management, and as such, a process to manage it needs to be established and integrated into operational processes. Success will be difficult if people and culture don't align with the desired ways of working. The team must be given training and help to be aware of the role security plays and how it can be integrated in a seamless manner. They need to understand how the benefits outweigh any perceived barriers, and in turn it needs to be demonstrated that these barriers either no longer need to exist, are minimized, or are within the gift of the team to reduce. Teams need autonomy, not bureaucracy. They need to be able to own solutions, tool choice, and be equipped with the knowledge of factors to consider. Continuous improvement helps everyone to perform better. We learn from our mistakes and are better for having experienced them. Education and opportunity to learn should be provided and seen as part of the system and program lifecycle. Collaboration between team members with different skill sets is crucial to increasing autonomy and secure deployments. When faults do occur, blameless postmortems are key to enabling lessons to be learned in a non-threatening environment. Everyone is more productive in a trusting, safe environment where they are encouraged to innovate and explore. Take time to prepare security requirements based on understood threats and risks. Build the system in such a way to counter and overcome these. Security epics should be seen as first-class citizens and added to overall project backlog for tracking. This is aligned with the NIST framework identify function. By considering threats and risks, a system can be architected with them in mind. Checks can then be put in place to measure the success of the design and help ensure compliance and security. With new regulations having come into force regarding data protection, such as GDPR, businesses need to plan to protect themselves and their subjects' right to privacy. The code and build phase is where security and component creation combine. It's where the benefits of a shift-left strategy with security as code integrations can be truly experienced. Getting real-time feedback on vulnerability and code weakness at development time empowers the developer to make informed decisions and resolve issues before code is committed. Security engineers can provide guidance on best practice for application coding, and infrastructure configuration can help reduce flaws and take on remedial action to fix bugs found in subsequent test phases. Imported code and components should also be checked for vulnerabilities early in the lifecycle to enable quick and concise remedial actions to occur. Shift left is central to the desire to fix issues earlier and reduce the cost of doing so. Initial vulnerability checks should be performed before committing code. They can be rechecked at build time with the ability to block use of components with severe vulnerabilities. It is also possible to monitor release components that reside within a repository to update the stance of their use. Additional testing, as we have discussed in a previous lesson, like white box testing or black box testing, may be performed as required. Automated security checks should feature during test and compliance checks with the ability to build upon the static tests performed locally by developers and during build time. A comprehensive set of integrated and automated tests can provide a pipeline with continuous assurance, facilitating continual confirmation that system changes haven't impacted the system's ability to meet its security and compliance requirements. This in turn reduces the risk associated with component changes and deployments, along with providing real-time assurance reports to risk managers. A comprehensive set of automated tests and checks will build on those performed by developers during coding and continuous integration. Automated testing should exhibit a downward trend of vulnerability and flaw discovery, as the shift-left approach will have empowered the developer to discover and take remedial action before the commit. Automated security testing will reduce the requirement for manual penetration testing. However, a comprehensive and effective approach to secure system creation is likely to see their inclusion for the foreseeable future. Component security status can change after release. Continuous monitoring enables the program to respond to changes and enforce policies on future deployment. The dynamic nature of cloud changes the way in which deployments occur, as well as their frequency and the frequency of decommissioning. Whole environments can be created and destroyed numerous times within a day. They need to be both created and destroyed in a controlled, secure manner. This process must factor in data cleansing and retention. Asset destruction needs to hold up to scrutiny and should be certified. When components are released following successful testing, continuous component scanning in program registries and repositories enables up-to-date assessment of vulnerability and licensing. This information enables decisions based on the current status of the component and limits its future deployment. Output from registry scanning will also inform teams if remedial action is required, rather than awaiting vulnerability scans taking place in production. Release components are versioned, and this detail is stored in a component management database, or CMDB, to keep record of current environment state. This in turn can be used in reporting and security auditing. Without an inventory, you cannot secure anything. You have to know what it is in the state. Gain full control over the deployment process by using a toolchain as the sole deployment mechanism. Ensure a repeatable process for creation and destruction through the use of a parameterized infrastructure as code patterns using centralized KV and secret stores. In the era of cloud, components should be treated as cattle, not pets. We destroy and create immutable images to meet our needs. IAM controls help control who or what can control and instruct services in a regulated manner. SaaS offerings that store data will likely have different procedures to be considered with regards to data disposal. Security and operations are combined throughout the operate and monitor phases. Visualization of the state and components within adds context and clarity. It helps with detection. If you don't detect it, you can't fix it. Operations security integrated with a system will help to ensure the security health of the system is as good as it can be with up-to-date information. Playbooks as code can be utilized to remediate and report on issues as they are detected. They can be run manually with a goal to automating their response to an issue. Standardized playbooks drive response and recovery efforts in a controlled, measured manner to reduce collateral damage and dormant attack vectors. An effective security operation will also include the rotation of secrets, revalidation, and inventory maintenance. Within the secure operations operate and monitor, it's not a question of if you get hacked, but when. Some key terms are RASP, which is Runtime Application Self-Protection, which is a security technology that uses runtime instrumentation to detect and block computer attacks. There's also the blue versus red team game days. Blue team members are the internal cybersecurity staff, whereas the red team is the external entity with the intent to break into the system. Another thing to look at is mean time between failures as well as mean time to repair. And we should also look at security orchestration, automation, and incident response, or SOAR. It is important to have DevOps and security work together early. DevSecOps can reduce risk and cost, increase quality, improve team synergy, enhance visibility, meet compliance, accelerate development, and secure rapid innovation.
All right, thank you for joining everyone. My name is Ron. I'm Ron Craig. I'm the program manager for secure engineering. First question I think we should ask ourselves is, what if your security defect became famous? As you guys know, starting with Heartbleed and Shell Shock around 2014, the big thing now is for security bugs to get their own website, to get their own snazzy name, and to get a lot of press. And security issues have been, becoming really a boardroom issue. And we've seen a lot of things with WikiLeaks and so on. And the field for security research is really expanding. And the best way for someone to make a living at this is to cash in on fame like this. So the people who found Heartbleed or Shell Shock or the recent Spectre and Meltdown issues, those folks, they face some financial security. A lot of folks are trying to start up their businesses on security research. And so the number one way to do this is to find bugs in software, security bugs. The number one goal in your life, if you are a security researcher, is to find a big security bug in, one of these security vendors' flagship products, and that will set you up. These bugs are sensational, and they have a tremendous cost, really, for our customers and for us. And don't forget, too, that security breaches can lead to litigation. One of the main things, though, that remind everyone is that the Federal Trade Commission in the United States watches any company that has some claims about the security of their software. And if the Federal Trade Commission decides that you have overblown the security claims, then they will come in and be very happy to institute what's called a consent decree. And since 2000, I've seen over 45 just for insufficient security practices. And here lately, those consent decrees tend to run about 20 years. And what that would mean is the U.S. federal government would come in and dictate exactly how we run our security program. As you can imagine, management is pretty keen that that not happen. So one of the ways we do that is make sure that the security of the software that we have is real, it's effective. So next slide here. What me worry? Absolutely, you should. Just a quick collection of some facts here. The Ponemon Institute does a study each year. The last one that I've got right now is from 2017, where they were estimating $141 per record. Average for a data breach, 3.62 million. Something you may not be aware of is that there is a growing black market for zero-day vulnerabilities. And what this means is over on the dark web, there are companies, individuals, crime syndicates that are watching for vulnerabilities, look for vulnerabilities, and if they find them, there's two things you can do. You can responsibly disclose those to a vendor, let us fix those, and then take some credit for it once the fixes are available, or you can hold on to them and sell them to a rival nation state. A vulnerability that we learned about a few weeks ago found the price for that was between $5,000 and $25,000. So you can make some serious money if you decide that that's your inclination rather than doing responsible disclosure. And we have these breaches, and everybody's heard about this, but the question is, have we really learned our lesson? A couple of quick examples here. Trend Micro is another cybersecurity vendor. And a couple of researchers decided to concentrate on their security products. And in 6 months, they found 223 vulnerabilities. In fact, the person who used to have my role thought that was such a challenge then to go try to help Trend Microsystem that he went over there to help them do the same sort of thing that we're doing with you now, to try to raise awareness and help make sure that our developers can, in fact, do a good job with the software that we put out. And then don't forget Equifax. I was affected by that. Many Americans were. And that was a relatively minor vulnerability in an open source package. And we use open source very extensively. And one of the things we're supposed to do is be scanning that for known vulnerabilities. And this was a known vulnerability. But the folks that applied the patches and so on there, they didn't get to it. They were going to handle it at the start of the next quarter. Unfortunately, meanwhile, the hackers were out searching websites, looking for any websites that had that vulnerability, and they found Equifax. And as a result of that, the CEO, the CIO, and the chief security officer all lost their jobs. So it gets to be a big deal, and I hope you're convinced there that that's an important thing that we should be avoiding. All right, so in this series, we're going to tackle a number of different types of issues, and I wanted to try to take a moment to explain why we chose what we've chosen. Cross-site scripting is the vast majority as far as number of vulnerabilities. And so that's why we started with this topic. The vast majority, and certainly anything going on the cloud, cross-site scripting tends to be the vast majority of what we see. And you'll see crypto vulnerabilities on here as well. OS command injection, SQL injection, those are very high severity issues. Even though their numbers are a little smaller, those kinds of issues are really serious. So the next presentation that'll be happening in July is on injection. So now that you're all sad and depressed, I'll say there's a good reason for this. Writing secure software is really not an easy task. You know, I was in development for 30 years, and we do face a lot of time pressure, lots of functionality you've got to do. You don't have a lot of time to do it, so you concentrate on making sure that the feature and function that you've been assigned gets done. Unfortunately, the hackers, they might have all the time in the world to sit there and to study and to analyze and to look for that one vulnerability or those one or two or three small vulnerabilities they can link together and use to cause some real damage. So not a lot of time. Again, as I said, our focus is really on the feature that we've got to get. Oftentimes security is not our primary focus. The hackers, meanwhile, they're looking for that one vulnerability. And then for motivation and resources, your developer is responsible for that product's primary functionality. And they're often not personally affected by product successes and failures. But the hackers, security researchers, those folks are motivated by bragging rights, by reputation, by making really some serious money, sometimes by politics. And, you know, they may be supported by nation states. So there's lots of resources behind there. You can't really blame, I think, some of these nation states for taking this approach, because in terms of where you invest your time and money, investing 30 years in universities and research programs and all this to come up with the technology you need takes a lot longer and a lot more money than it does simply to bring on some really good hackers and go steal it. So we have to watch for that. And then, of course, developers are asked, and we're asking them now to learn a little bit about security, enough not to introduce issues. But those hackers, they are specializing in security, looking at that very carefully. Again, with good security education, you do a good job with the design and implementation practices. It is not all doom and gloom. And how do we do that? So we've got several approaches here. Preventing new bugs. One of the best things I think that developers can do is know the SANS 25. It's there on the website. It's listed and laid out in 3 or 4 different ways, depending on how you learn best, how you remember things. It's really good to do that. Every year, every developer is supposed to go through the SANS 25 to make sure that they're reminded and keep in mind what issues they need to be watching for. You need to think like a hacker, which is one of the reasons for this presentation. Not just what are your use cases, but what are your abuse cases? What evil can be done against your application? And what could someone accomplish with that? And then building defenses into your software. The key ones are always input validation, output sanitization, strong encryption, strong authentication and authorization. If you handle those, I think 90% of the issues that we have will go away. And a lot of times, I'll see teams struggle. They maybe chose a framework that doesn't have a very good reputation in security. And so they are from then on forever trying to patch one cross-site scripting issue and then one more cross-site scripting issue, rather than choosing a framework that will provide cross-site scripting protection for the application. So if you try to do it, catch as catch can, somebody else is going to catch some things that you miss. Another thing that it's good to remember is, don't think if you're not internet facing, you're not at risk. The majority of breaches still are from insiders. So being behind a firewall, being inside the network is no defense, because sometimes the bad guys are on the inside. And then, same thing for files and databases. Just because they're local does not mean that they don't need to be protected. And then, so that's preventing new bugs. And then make sure you address the existing bugs. And sometimes it may make sense to redesign your product front end. Choose a new technology. The folks that used Struts 1 they've all had to move to another version. Some of them have chosen not to go to Struts 2, to go to something else. It's worth taking the time to look into the security features that are in the technology that you're using, and look and see what the history looks like for those. Implement architectural changes that can fix your security flaws at the top. If you can put in a layer that does validation, then if somebody forgets to do validation at some particular point for some particular parameter elsewhere, you're better off than if you're depending and counting on everyone to think of everything every time they write something. And the same goes here. Don't spot fix your issues. See what you can do. And then please recognize that security bugs are special. Yes, they're software bugs, they're software errors, but they compromise your customers' data. And they are sensational, and they can show up in the press, and they can cause real problems. So a lot of teams like to, we'll deliver next quarter, so we're going to get an exemption or an extension. Really look at those things and think hard. It may not be very wise. That's what Equifax did. And the C-suite was basically empty because of that.
So let's start with the definition. What is cross-site scripting? Cross-site scripting is a type of vulnerability that allows unauthorized person to inject client-side script or scripts into your web application. And these malicious scripts, they can come from anywhere. Most commonly, they come as part of HTTP parameters when somebody fills out a form on your website, for example. But they can come from other sources, HTTP headers and cookies. They could hide in JSON and XML files that you exchange with the front end. They could embed themselves in databases or other types of files uploaded by users. So you really have to watch for these and be ready for them to come from any source that's user controlled. As Ron mentioned earlier, cross-site scripting is the type of vulnerability that we see most often. So what are the dangers of cross-site scripting? They can be used for a whole lot of malicious things. So first of all, they could be used to harvest your credentials. Attackers could take over user sessions. Cross-site scripting can be used to facilitate cross-site request forgery. They can steal your cookies or data that's stored locally. They can be used to elevate privileges, and also can be used to direct users to malicious sites. So as you can see, there's a lot of damage that can be done. The cross-site scripting is seen across the board. Here you can see two pretty famous products, WordPress and Drupal, and statistically, cross-site scripting is the highest occurring vulnerability in both of those products. Also, a few years ago, risk-based security company did a study of what types of vulnerabilities are most commonly occur, and they did that based on internet database that stores information on known vulnerabilities called VulnDB. And as you can see in this graph here at the bottom, the blue bar shows how frequently the cross-site scripting vulnerabilities are found. And the data is from 2007 to 2015, and most quarters, it's the highest occurring vulnerability for all kinds of products. Cross-site scripting is not only found by QA teams or penetration testing teams, they're actually actively being exploited by attackers. So there are two prominent recent examples. One was where eBay was attacked with phishing attacks based on cross-site scripting, and Apache Foundation was hacked. And in the kill chain there, the first step was exploiting cross-site scripting in Jira. And there are many other examples. So it's not surprising that this vulnerability shows up on the top 10, OWASP top 10 web vulnerability list. If you're not familiar with this, I highly recommend checking out OWASP, which is an online community for web application security. And as a developer, be aware of this list and consult with it from time to time to make sure in your code you're not introducing these vulnerabilities. And also another list that Ron mentioned, SANS top 25. Cross-site scripting is in the 4th place on that list. So it's very dangerous. So let's take a look at how cross-site scripting actually works. We'll use a very simple example of an application you're developing that has simple data entry. So in this case, we're entering user information. So let's say we have a very simple form. We enter full username, then username, password, and the role. And the users that are entered are displayed in a simple table. For this example, we'll use Java server pages, but you can really get cross-site scripting with pretty much any technology or framework. So if the rendering code is simple, if we don't have any extra checks, if we just basically reflect back whatever data that was entered, the output will be unprotected. And I'll show you how in a second. Regular data input will not cause any problems. So user enters the name, the username, and other information, and the generated HTML will just basically reflect what was entered right back. We'll assume that there is some kind of a database behind this application. The data is stored there, and every time you visit the list of users, you get a nicely formatted HTML page. So far, so good. Suppose there is a malicious user that decides to enter something more than just the full username. Let's say they enter an HTML tag, in this case script, and a piece of JavaScript code. Because our application does not have any special defenses, neither on input nor on the output, the data that was entered will be stored as is in the database and will also be rendered as is when it's time to render the list of users. And because there was no special processing, the tags, the HTML tag script that was entered will be rendered as is and will be interpreted as is, as a script tag by the browser. So at the bottom here, you see the actual example. Because it's a script tag, the script will fire and the dialog box will pop up. This is definitely not what the developers of the application intended, but this is something that the user was able to do. So it seems like an interesting trick, something to show to your friends, but is it really harmless? Unfortunately, it is. It's very dangerous. If you think about it, essentially you're letting unauthorized person inject functionality into your application. And that functionality could be anything. It most likely won't be something as benign as what I showed in the previous slide. And another danger here is that your customers, as they're using your application, they trust it. And this trust automatically now extends to this code that a third party has injected. Once the record is added, in this particular case, it'll be stored in the database. And every time the list of users is rendered, this dialog box will pop up. This is actually an example of something called stored cross-site scripting, which is a more dangerous variant compared to reflected cross-site scripting. Stored cross-site scripting is retained by the application and usually affects more than one user. And the added danger here is that that other user that this malicious script affects may be application administrators. You could actually get privilege escalation out of this. Somebody could take over an administrative account. Reflective cross-site scripting is a little less dangerous. It's usually sent as part of email or embedded in a malicious link, and usually affects just one user. So let's look at a more sinister example and see what actually can be done with cross-site scripting. So let's say malicious user enters his name, but also adds this blob of HTML and style sheets and JavaScript, and see how it will actually be rendered in the client application. So when the list of users is rendered, now there is a dialog box popping up saying that the session has expired and asking user to enter their credentials. So we now have a very serious security issue. Some users may actually fall for it. If attacker tweaks the style sheets to be just right and match the overall look and feel of the application, a lot of users may actually think that, yes, my session has expired, I better log in. And they will enter their username and passwords, which will then be taken by the attacker and used, first of all, to log into the application. They can become you, they can impersonate you. And also, as we know, users reuse their login credentials on multiple sites in multiple applications. So this credential harvesting can actually be used elsewhere in your banking application or in any important application in your life. So as you can see now, this has become a very dangerous situation. It must be mitigated. It's actually not very hard to prevent cross-site scripting. You just have to be careful when you develop code. Output encoding works very well, and it's quite effective. For HTML, you use HTML encoding. For cross-site scripting that comes across in URLs, you could use URL encoding for special characters. How does it work? In HTML encoding, if you just render data as is, like in this example for test text with surrounded by the bold tags, when the browser sees that, it renders that as the bold text. However, if you were to HTML encode, which means that you would replace characters that are significant to HTML format with what we call HTML entities, this input will no longer be considered as valid HTML. It will just become harmless text. And as you can see, if we replace angle brackets programmatically with corresponding HTTP entities, which are %LT semicolon and %GT semicolon, then the browser will actually render the string exactly as it was entered by the user, and it will no longer have that special meaning. It will not be interpreted as HTML or JavaScript. Of course, as with everything, there are special cases. There's something to watch out for. Encoding may not help in some corner cases, such as UTF-7 encoding. It's a pretty rare type of attack, but to neutralize that particular case, you also have to watch in what encoding you render your pages. So if it's UTF-8, you have to actually force that in order for browser not to kind of automatically recognize UTF-7 encoding and trigger cross-site scripting if it's there. So going back to our example, how do we fix it? There's lots of functionality for escaping and properly neutralizing dangerous output. So in this particular case, there's a Java function in screenscape utils class called escape HTML. And if for every field you use that, all the special characters that user may have entered will be properly replaced with HTML entities. And as you can see at the bottom, the text displayed will be exactly as the attacker entered it. It will not look nice, but it will lose its special meaning. It will no longer be interpreted as HTML and embedded JavaScript. Escaping HTML characters is only part of the problem. Sometimes cross-site scripting may show up when you let user input actually appear as part of JavaScript code that you are generating. So in this particular case, the variable particularly input variable that user specified, search, is set to a cookie, but nothing is done to neutralize possible malicious input there. And an attacker may add an alert JavaScript function and surround it with single quotes, which will let them break out of single quotes in the code and make alert function actually execute. So when you're rendering user data as part of JavaScript that you generate, you also have to pay attention to this and escape things like single quotes, as shown in the example at the bottom. In modern applications, we use a lot of rich client UIs, and unfortunately, often they are built using unsafe handling of DOM, document object model. And in particular, there is an attribute in the DOM model called inner HTML. Anything that you put in there will be interpreted as HTML. So if somehow user input makes its way into that attribute, whatever was in the user input will be interpreted as HTML, and also corresponding JavaScript if there is some embedded in there. Like in this example, there's a response text variable that comes from the user. If user embeds an invalid image tag specification in there, the on-error handler of that specification will fire and it'll execute the alert function. Of course, in the real case, the JavaScript functionality will not be as benign. So in such cases, it's important to pay attention and use safe alternative to inner HTML, which is text content attribute or inner text in some versions of Internet Explorer. There are also special cases where you could use JavaScript eval function. Eval is really a dangerous, very powerful function that will essentially take whatever input you give it and interpret it as JavaScript. We would like to strongly discourage use of this function because a lot of things could go wrong. But if it's unavoidable, you have to really carefully scrutinize what goes into the input of that function. And same goes in general for generating pieces of JavaScript dynamically. It's something that's quite dangerous if you don't do it correctly. So it's best to keep the data that comes from the user and your code separate as much as possible. And below, you see a particular example of what could happen if you were to take eval function and just, with any sanitization, use the input that user provided in it. Output encoding is only part of the solution. Another important thing is input validation. You really don't want malicious data entering your product. There are different ways of doing input validation. The one that we recommend is called whitelisting. And as the name suggests, in this particular case, you build a list of, hopefully very short list, very restricted list of either set of characters that you would like to accept, or a set of strings that you would like to accept, and then prohibit anything else that shows up. This will reduce the attack surface to a known quantity. You know exactly what you're dealing with, and you reject all the other input. If possible, most input should be whitelisted to a really reduced set, like alphanumeric. I think in most data entry, that's enough. There are special cases where you need to allow single quotes or other characters, but really, special characters should be allowed in on an exception basis, and you really have to think carefully, do you really want to allow a particular character into your application? In our testing work, we see other ways being implemented. Blacklisting, which as the name suggests is the reverse of whitelisting, it's really not effective. If you implement a whitelist, you basically are saying, I know this particular types of malicious output, I don't want to accept that, but I'll accept everything else. And as you can imagine, you're dealing with unknown quantity. You're dealing with the whole universe of possible inputs, some of which may be malicious, but you just don't realize that they are. There is a very interesting page that I really recommend all developers take a look at, which is OWASP cross-site scripting evasion. And when you look through it, I think you'll be unpleasantly surprised by the sheer number of different patterns, different ways to bypass whatever blacklist you've put into your application. There are a lot of really smart people out there that really can, wreak some havoc and it's really not recommended that you take this approach, that you use blacklisting. We also, from time to time, see client-side input validation. This is where you basically embed JavaScript code in the browser, and as user enters the data, you take the value and you check whether it's valid or not, and reject something that's not valid. It's very good for user friendliness, for product usability. Unfortunately, it does nothing for product security, because very often attackers won't even be executing their attacks from the browser. They'll be using so-called attack proxies that go directly against the server. So your JavaScript functionality that you implemented in the browser to check the values won't actually be even executed. When you protect your application from malicious input and encode the output, I really think you should implement both approaches. This is something that we call defense in depth principle. There's a chance that, let's say, one of the two mechanisms has a bug in it, but in that case, the other one will take over. If you have multiple layers of defense, there's a higher chance that one of them will be solid and will actually protect your application. So implementing many mechanisms is better than choosing just one. When you implement the input validation or an output encoding, try not to roll your own functionality. It's not easy to do it properly. It's very easy to make a mistake, to forget some edge case, and that's all the attackers need. They just one case to get into your application. There are proven libraries out there in many languages, and when you use proven established functionality, a lot of people have already used it. Probably a lot of bugs have been found and fixed. So you're really better off using something that the industry uses rather than something you just wrote yourself. It will be safer. And also, as Ron mentioned, I want to reiterate that we in our code reviews, we see a lot of places where people just pepper their code with different checks, and that's really an unsafe approach. It's very easy to miss just one place where you check for malicious input or where you do not encode the output properly, and your application could be broken into. It's much better to build a framework where, let's say, you have your validation functionality in one place and it's called from everywhere where you accept input, and you encode your data that you output in one place. And that way it's much easier to maintain. It will be a tighter code. And if you have a case where, let's say, a new developer joins your team, or you're a seasoned developer but just forget to put some check on some input field, if you have a framework that protects you, you will still be safe. It will not hinge on the skills of individual developer. So to summarize, please encode all data output that you generate as part of HTML or maybe some dynamic pieces of JavaScript that you generate. Please use strict whitelists on accepting the input. We do not recommend using blacklists or client-side validation. These methods are just not that effective. And finally, try not to roll your own functionality, but rather rely on proven libraries. Of course, we're just scratching the surface here. It's a much broader topic. There are a lot of details to be aware of. So in the slides, we listed a number of links that you can check out to learn more.